There's nothing more rewarding or exciting or, quite frankly, more societally important than inventing. And the key thing is persistence and being able to stick with your ideas and continue to pursue them relentlessly.
At John Rogers Lab at the University of Illinois, his team is pursuing lots of ideas simultaneously. In fact, it's hard to know where to look first. From medicine to photovoltaics to microscopic printing techniques to LEDs, Rogers is reshaping ordinary materials to help address some of society's most pressing needs.
If you look at biology, it's inherently made of materials that are soft and curvilinear. And if you compare that to conventional electronics, you have a huge mismatch. And so we've been addressing that problem over the years, is how do we take a form of electronics like this and make it truly tissue-like?
Rogers' solution? Developing techniques to slice silicon into ultra-thin, flexible sheets.
So if you take these nanoscale membranes of silicon, you can put them on a sheet of plastic and make a bendable piece of electronics in that way. Two specific examples involve applications in cardiology and neurology.
In cardiac surgeries, his monitoring devices actually bond to the heart surface.
Almost like a piece of saran wrap. This device provides a window into regions of the heart that might be operating in an aberrant way.
In neurology, this same technology helps surgeons treating patients with epilepsy.
Instead of mapping electrical activity on the surface of the heart, we're mapping it directly on the surface of the brain. The electronics conformally wrap and drop into these deep fissures and folds that allows very precise high-resolution measurements of the electrical activity of the brain. Or how much smaller we could make the cells.
Tackling another of society's most vexing issues, energy. Rogers turned his attention to the kinds of wafers used in photovoltaic arrays that turn sunlight into electrical energy.
What would happen if you took that wafer and in a controlled engineering manufacturable way exploded it into a billion tiny shards, spread them out in a low aerial coverage on a plate of glass, and then mount tiny ball-bearing lens optics on top of each one that have the effect of focusing very tightly incident sunlight onto those very tiny solar cells. And when you wire them all up together, you can generate tremendous amounts of power that way in a very cost-effective manner.
But wiring them together required special manufacturing tools. So Rogers and his team developed a printing technology to essentially write with silicon.
So we use very fine capillary nozzles, and by moving the stage around and controlling the voltages that we're applying to that nozzle, we can directly write those interconnect lines that tie these cells together in an electrical sense.
Another project of the Rogers Lab is developing low-cost digital cameras that mimic the human eye.
We configure arrays of silicon photodetectors on a hemispherical surface with about the same size and radius of curvature as the human eye. And if you do that, it turns out you can achieve a very wide-angle field of view, very low aberrations, very uniform illumination, even with the very simple, low-cost, lightweight imaging optics.
In his myriad scientific pursuits, John Rogers maintains his curiosity and excitement about the inventive process.
The laws of nature aren't simply a set of parameters that constrain the behavior of the natural world, but it's a set of tools that allow you to predict the future and engineer the world for favorable outcomes.